Here we go. The next obvious step in our study of parametric equations is to do some calculus with parametric equations, as we will do next. Oop, there we go. Now let's get this thing up to full screen. When we do calculus with parametric equations, there's really nothing new. But we're going to do a review. Calculus with parametric equations, which will really just amount to a review of basic calc topics. And those topics will be list slopes and tangents, and then we're going to talk a little bit about curvature, and then we're going to talk about area under a curve, and finally we'll talk about some surface area. And when I say surface area, it's the surface area of a solid of revolution. My handwriting's a little off here. Solid of revolution. Okay. However, there is one kind of, let's make a note here in blue. There's one kind of new topic under the area under a curve section. All right, so the first one will be, well, let's pick an example actually. We'll do that here. Pick an easy example to work with, so we can kind of relate this all back to the previous section. Pick an easy example with which to work, all right? But whatever, this is not a grammar class. And we're going to pick the one that's almost cliche. I'm going to say that x equals t, y equals t squared, and then we're going to take this from negative infinity all the way to positive infinity. All right, so what does that thing look like? Well, we have a set of axes like this. That's x, that's y, and then as t is x, you know, x is just going to kind of move along like this, and y is t squared, so y is going to start up here and go down like this, and go up like that, and we know that's going to be a parabola. Boy, that is a terrible parabola. But I'm going to let it go because I don't want to stop and edit it out. So let's take a look at slope. Right, and remember from way back when you took your algebra class, your very first algebra class, what is slope? It's rise over run. Or it equals some change in y over some change in x. Fine. But what about with respect to, that means with respect to, I think you've probably seen that in a math class, t, the variable t. I'm interested in how much y changes, so the change in y is going to be the rate of change of y over the change in t, or this is the rate of change times dt, right? So the change in y is dy dt times dt. That works out algebraically on this side, but it should make sense. This is the slope times how far we traveled in the t direction. Likewise, the rate of change of x, or the change in x, is the rate of change of x times how much did t increment, the increment in t. So it's dx dt times dt, same thing. Now, we can also keep in mind that these guys up here, this x of t, we can also call that kind of a f of t. And then this guy here, we can kind of call that, or at least the Thomas book calls that g of t. All right, so another way to look at this is delta y is dy dt, which is g of t, or g prime times dt, and this is f prime times dt. Okay, so let's put that together. And we'll get back to this pen. That the change in y over the change in x is going to equal dy dt times dt over dx dt times dt. Now we haven't used this one in a while, so it's very exciting to do. You know, the dt's go away. So I can say that the slope, right, of the tangent line equals dy dt over dx dt, which equals y, remember, is also called g prime of t over f prime of t. The book we're currently using calls y g and x f. But we have to be very careful here that dx dt is not equal to 0. Why is that? Because that would give us, first of all, a division by 0 problem. But second of all, what does that really mean? Dx dt equals 0. So as I'm moving along, as t is stepping forward, my x is changing, my y is changing. If my y changes and my x does not, what kind of line does that give me? So what does this mean? And I'm not talking about the double rainbow. What does dx dt equals 0? What does that mean? So that's something to keep in mind. All right, so that's all kind of first derivative stuff. Now we're going to look at second derivative. Or curvature. What is that? Well, the second derivative as far as curvature goes is d squared y dx squared. Another way to write that would be the derivative with respect to x of dy dx. Right? Or another way to look at that is the derivative with respect to x of y prime. So three different notations here. They all mean the same thing, but it's useful to kind of move back and forth between notations. We know that this guy here, y prime, is what we just had up above, which is dy dt over dx dt. So that'll be y prime of t, like that. So the second derivative, moving down this way, equals the derivative of y prime, so d of y prime all over dx, right? But remember that these are both functions of, since these are both functions of t. In other words, it's the derivative of y prime of t over the derivative of x of t. Boy, my handwriting is terrible today. I'm out of practice with this thing. It's going to look like dy prime dt over dx dt. So I will, well, I've got a page to kind of burn before the next topic, so we'll sum this up. That the second derivative with respect to x of this parametric equation works out to be the change in y prime with respect to t over the change in x with respect to t. And we'll do some examples that are related to that. So that gives us kind of we've summed up the first half of Calc 1, which is derivatives, and in just a few minutes. So now we can kind of go back and do sum up integral calculus with respect to parameterized curves, and we'll look at the area under a curve. And we'll look at our example like that, and remember that our function was this parabolic looking thing that goes roughly like that. And we're trying to find some area under this curve, and let's sketch that out in orange. So we're trying to say, let's say all the area all the way up to here, if we're trying to find this area, trying to get all this. Really what is that going to be is a bunch of little rectangles. We need to remember that from Calc 1. And we're trying to find all this area. Well, the area of this little guy the area of that rectangle equals the height, which is, I'm going to get really crazy with colors, which is just y of t, and then times the width, which is dx, right? So in terms of this rectangle again, we've got the height times the base. The height we know is y times the base, which is dx. Well, what is dx really? We know that, go back to my black ink here, that dx, the change in x, is really the rate of change with respect to t times dt. Right? So that's a little change in x. So the area equals area of one rectangle equals y of t times dx dt times dt. Now that seems kind of silly. Why did I write dx as dx dt times dt? Well, another way to write this using our function notation would be y of t is simply g of t, and dx dt is the derivative of the x function, so that's f prime of t times dt. So that's the area of one of these little rectangles here. Now, if we want to get the area of the whole thing, the entire area, we know the area of one little rectangle, and I think we have to define some limits here. Let's say we want to go from A to B. Let's call this A, and let's call that B. We would do the area equals the integral from a to b of g of t, or that's, remember, y, times the width of these rectangles, which is f prime of t times dt. Right, so f prime t dt is really this is the width. So I said that kind of wrong, so I'm going to annotate this to get it right. This little blue part here is height, and this little part here is the width. Okay, so that's height and width, and that gives us the sum of the area of the whole thing. Let's do one quick example using the function that we picked. If I wanted to find this, y equals, or x equals t, y equals t squared, and I wanted to say we're going to go from 0 to 3. Well, what do? We'll just go from the integral. Now these are not x values that I'm putting here. I'm going to say the integral from t equals 0 to t equals 3 of the y function, which is t squared, times the derivative of the x function, which is 1, times dt. So that equals the integral from 0 to 3 of t squared dt, and we know that that will equal, let's see, raise the power by 1, divide by the new power, so that's t cubed over 3, and we'll evaluate that from 0 to 3, and so that gives us 27 over 3, right? Minus 0 over 3 equals 9. Right, so it's very, very similar to what we do over here. Well, I'm not even going to say it's similar, it's the same. It's just we have to write things in terms of t, the height in terms of t, the width in terms of t here. That's what that is. All right, so that is area under the curve. The next thing we'll look at is the arc length that's not I spelled that wrong. Sound effects are important. L-E-N-G-T-H, length, or length along the curve. So I guess we would call it curve length too. Now remember that, because I don't have it on this page, x equals some function f of t, and y equals some other function g of t. And I just noticed, this is probably completely coincidence, maybe not, that x looks a little bit like the very letter f, and y, at least with my handwriting, looks a little bit like g. I don't know, it's kind of, sometimes you notice these things that are completely irrelevant, but you feel like pointing them out. So we know that this is x and this is y, and so say we have some curve that kind of cruises along like this, and we want to find the length of some section of this curve. So let's say we'll do that in green. So I'm interested in finding this length of that curve, and I'm going to linearize that, basically. So I'm going to make a little bitty right triangle here. I'm going to call this my delta y. Did I call that delta y? Or dy. And I'm going to call this thing here dx. All right. Well, what is dy really equals, we've been through this before, is the dy dt times dt, and dx equals dx dt times dt. Right? So it's the kind of the rate of change of t times how much did t change. So that's dx and dy. Well, if we call this ds, right, a little increment of length along this curve, we could say that ds squared equals dx squared plus dy squared. Well, that's nice, because we know what dx and dy are, so we can write that. Dx is dx dt times dt, this whole thing squared, plus dy dt times dt, this whole thing squared, right? Well, so this will be, we've got dt squared here, so we can rearrange this guy a little bit and just say this is dx dt, or that could also be f prime squared plus dy dt squared, and we can take this whole thing and multiply this by dt squared. And what is this equal to again? This is ds squared. So when you take the square root of it, I'm going to conveniently switch back to my black pen here. We know that ds will equal the square root of dx dt squared, dt squared plus dy dt squared. I should put that in parentheses just to make sure you know it's not just the dx squared, but that wouldn't make any sense. Dy dt squared, and that's the end of that. And because when we take the square root of the dt squared, this just becomes a simple dt, which will be very convenient later on, that we can replace the x function and the y function with, instead of increments in x and y, we have a little increment along the length of the curve. So that's going to be pretty handy later on. So this is ds dt squared. Now, if you remember the fundamental theorem of calculus, we talked about that back in Calc 1. We talked a little bit about it in Chapter 8. But if we wanted to write arc length as a function, in other words, how far have I traveled as a function of t? I could write this as, my length as a function of t equals the integral from starting point A to t. So anyway, so if we want the arc length as a function of t, like kind of our cumulative length, the length at time t equals the integral from starting point to t of, how do we do this now? The square root, ooh, that's a horrible square root. I'm just going to save time, parenthesis f prime of tau. Now why do I use tau? Squared plus g prime of tau squared times d tau. Why do I do that? Because I can't, I've got t as a limit of integration, so I can't use t again in here, so I have to call my parameter tau and my limit t. So I'll be slowly kind of moving along, at whatever point t, I'll be at this arc length. So that's what that is. Now, according to the fundamental theorem of calculus, if I want my ds dt, it will just be the derivative with respect to t of whatever function this generates, a to t of the square root of all this stuff, d tau. Well, I know that when I do this, I just get my integrand right back out of it, so that my ds dt is going to equal the square root of all this stuff. So my arc length parameter, which I call ds, an increment in the direction of travel will be the square root of this thing, but this time I'm going to write it as dx dt squared plus dy dt squared times dt, right? So that means if I'm trying to do something, I'm trying to keep track of where I am. Like I want to keep track of how much material I've laid down. I want to keep track of how much mass I've accumulated or how much heat I've generated along a wire or something like that, along some little incremental length. I can replace that with my parameterization pretty easily. So very, very useful in many physical science applications. Well, it may be useful in other applications, but since I'm a mechanical engineer, I don't know them. All right. So finally, page 9 already. This one's getting long, guys. Sorry. The last thing we're going to cover is the surface area of a solid of revolution. The surface area of a solid of revolution. Side note, one of my favorite bands is Queensryche, and one of their greatest albums is kind of like a story rock opera, like epic, called Operation Mindcrime, if you ever go to check out. But it's all about revolution. And whenever I say revolution in that tone of voice, I always think of this sweet album from when I was a kid, high school age. All right, anyway, we digress. We're talking about tangents. I went off on a tangent. We're supposed to be talking about a solid of revolution. There's x, there's y. Here's our profile. Let's do that in black, like this. It's this parabolic looking thing. And if I'm going to rotate that, around this axis, what would that look like? Let's do that in blue. So I'm going to rotate it around the y-axis. So it'll be this kind of parabolic looking thing. And then it's going to be kind of this shape over here, the mirror image. And it's going to rotate its way all the way back over here. All right? But if I just look at one little part of that, let's do that in orange. So if I just look at this little bitty thing there, and I'm just going to rotate that around, so it's going to rotate back behind, and then there's going to be a mirror image like thing over here, and that's going to rotate around like that, and then this is going to rotate down here like that. So what is this little orange guy here? Oh, look at that. That's a ds, isn't it? So that's one little piece of the curve. Right, so what's this area going to be? Let's call this a band. One band. That looks like panned. Band. My favorite band being Queensryche. See, I can tie this all together. So I've got this one band. The area of a band, well, that'll be the circumference of this thing times this little bit here. So it's like kind of one strip. So that would be 2 pi r times ds, because it's basically one long skinny rectangular band that kind of goes like that, right? Well, but I know that r is really the x position here, because r, the radius of this circular band, is x. So that equals 2 pi x times ds. But I know what my ds is. It's this square root thing from the previous page. So I know that the area of one band equals 2 pi x times the square root of dx dt squared plus dy dt squared times dt. Right, so that's the area of that. All right, well, if I want the area of the whole thing, the entire area, and again, I'll conveniently switch over to black. Well, I just take my individual one and I add up a whole bunch of ones just like that. So my area equals the integral from A to B, and again, these are values of t, remember, of 2 pi x times the square root of dx dt squared plus dy dt squared times dt. And this is for a revolution rev about the y-axis, or in other words, the radius equals the x value. Well, so you might imagine that it's similar the other way, that I could say that area equals the same integral of 2 pi y times dx dt squared plus dy dt squared times dt, and that's for revolution about x-axis, or, so if, remember, if I revolve this thing about the x-axis, the radius of each one of my little bands would be the y value. So the radius equals the y value. So that is pretty much everything you need to know in 20 minutes, 25 minutes. I've kind of lost track of time. Everything you need to know about using calculus on parametric equations, and I'll make another video with a few examples. If I don't have time to do that, then we will do some examples in class. So enjoy.